Next chapter, acids, bases and indicators. Now, citrus fruits such as lemons, oranges and grapes are sour in taste. These fruits taste sour due to presence of acids. Acids are also found in foods such as vinegar, tangerines, and tomatoes. Vinegar contains acetic acid. Tangerines contains tartaric acid, and tomatoes contain oxalic acid. Acids can usually be identified as sour-tasting substances. We also find substances that have a bitter taste. These substances are called bases. Soaps, detergents, and baking soda are some common bases. Identification of acids and bases in the laboratory cannot be done using testing method. We use indicators. A simple acid-base indicator can be made using extracts of flower petals. We add a small amount of isopropyl alcohol to a mortar, put some fresh petals and crush them using a pestle. We obtain an extract of the flower petals. If we add some drops of 0.1 molar sodium hydroxide, which is a base, the solution turns green. If we add some drops of 0.5 molar hydrochloric acid, the solution turns pink. Because the flower extract shows different colors in acid and bases, it's an indicator. However, this kind of indicator only works for a short duration of time, and the color keeps changing with time. So we need a more reliable and consistent indicator. We use commercial indicators. The commonly used commercial indicators are litmus paper, phenolphthalein, and methyl orange. Litmus papers occur in two main colors, blue and red. When a blue litmus paper is dipped in an acid, it turns red. When a red litmus paper is dipped in a base, it turns blue. Phenolphthalein is colorless in acid, while in base, it turns pink. Methyl orange gives an orange color in an acid, and in a base, it gives a yellow color. Universal indicator and the pH scale. So we can be able to tell if something is an acid, alkaline, or neutral by using an indicator. Indicators are substances that show different colors when they are in acid or alkaline solutions. Litmus paper is the simplest indicator that tells us whether something is acidic or alkaline. It is made from lichen, which has been used to dye clothes for hundreds of years. It can be used as a liquid or a paper. The paper is the easiest and more reliable. It comes in red litmus paper and blue litmus paper. So just remember, a red litmus paper changes color for alkali, and a blue litmus paper changes color for acids. However, litmus paper only tells us whether a substance is an acid or an alkali, but it does not tell us how acidic or alkaline it is. In 1909, a Dutch biochemist, Peter Sorensen, introduced a scale to measure the acid and basic strengths. The pH of acidic solutions is less than 7. pH of alkaline solutions is greater than 7. That of neutral solutions is 7. A universal indicator is a mixture of different indicators or dyes which has very many different color changes, and thus it shows us the pH value of a particular solution. Again, it can be used as a liquid or a paper. The pH runs from 0 to 14, with 0 being extremely acidic, 7 being neutral, and 14 being extremely alkaline. Stomach acid is a strong acid with a pH of about 2. Acid rain has a pH of about 5. Milk is neutral with a pH of 7. Seawater is slightly alkaline. Soapy water is a strong alkali, and bleach is a really strong alkali with a pH of 13. So the universal pH indicator is able to indicate the entire pH spectrum. Now, properties of acids. We start with reactions with metals. Now, in this experiment, we will add dilute hydrochloric acid to these pieces of metal in these tubes. Tin, iron, magnesium, copper, zinc, and calcium. So now we put some dilute hydrochloric acid in the first test tube, then iron, and magnesium, and then copper. We put in zinc, and finally in calcium. From the onset, we can see that the different metals react differently with the same concentration of the acid. We can see that calcium is the most reactive here, followed by magnesium and zinc in that order. Reactions of the other metals are hardly noticeable from far. If we closely look at copper, we can hardly see anything happening. The reaction is too slow. If we look at iron closely, we can actually see some bubbles on the surface of the metal. Again, the reaction is slow, but better than in copper. As for tin, really nothing can be seen to be happening. Too slow. And so dilute acids react with metals to form a salt and hydrogen gas. The evolution of the hydrogen gas is what causes the effervescence. The reactions can be represented by the equations shown here. Highly reactive metals such as sodium and potassium react explosively with dilute acids. Let's see a reaction of sodium with sulfuric acid this time. We have a sodium metal on the table, and we transfer some dilute sulfuric acid into the beaker. And then we will put the piece of sodium metal into the acid. As you can see, the reaction is very vigorous and can be dangerous. A lot of heat is being generated. How about potassium? Again, we have potassium metal on the bench, and we add 5 milliliters of dilute sulfuric acid into the beaker. And now we will carefully put the potassium metal into the acid. And you can see the metal's shiny surface is already fading due to reaction with oxygen in the air. The reaction is much more vigorous than in the case of sodium. It generates a lot of heat, which ignites the oxygen gas being generated. And again, we can see that potassium is more reactive than sodium, which is more reactive than all the other metals we had seen before. So you can see that hydrochloric acid produces salts called chlorides, and sulfuric acid produces salts called sulfates. Nitric acid and carbonic acids will produce nitrates and carbonates respectively. From our experiments, we can arrange the metals according to their order of reactivity with dilute acids. This is called the reactivity series. Next is reactions with carbonates and hydrogen carbonates. Now in this experiment, we will react zinc carbonate with sulfuric acid. We add 2 spatulas of zinc carbonate into the test tube, and then we add dilute sulfuric acid. A reaction is taking place and a gas is being produced. Warming will speed up the reaction. When the gas is bubbled through lime water, a white precipitate is formed, indicating that it's carbon dioxide. The reaction taking place can be represented by this equation. And so acids react with carbonates and hydrogen carbonates to form salts, carbon dioxide, and water. Reactions with bases. Now, reactions of acids and bases are called neutralization because the resulting product is a neutral one. Bases that are soluble in water are called alkali. For example, let's take 10 milliliters of sodium hydroxide, which is an alkali, in a beaker. To this solution, we add a drop of methyl orange indicator. The solution turns yellow in color. Now we add a few drops of hydrochloric acid to the solution and stir continuously. We continue adding the acid drop by drop and keep stirring until the point where the color of the solution changes to pink. The change in color indicates that the added acid is just enough to neutralize the base. This is called the endpoint. During neutralization, the solution generates heat. If you heat the solution and evaporate the water, you will remain with salt, though it's contaminated with the indicator. This salt is sodium chloride. The reaction can be represented by this equation. And so in general, acids react with the bases in a neutralization reaction to form salt and water. Now let's react an acid with an insoluble base. Let's see a reaction of copper 2 oxide and sulfuric acid. This black solid is copper 2 oxide, which is an insoluble base. We add to it a small amount of sulfuric acid and warm the mixture. From far, we can see a blue solution being formed. By now, you know that is copper 2 sulfate, which is a soluble salt. Again, dilute acids react with insoluble bases to form salt and water. Acids have many uses in life. A dilute solution of hydrochloric acid is used for removing deposits on the inside of boilers. This is called descaling. Sulfuric acid is used in the manufacture of fertilizers such as ammonium sulfate and also in acid batteries. Nitric acid is used in purification of metals such as gold and silver. Bases are mostly used as laboratory reagents in industries and also for our daily activities. Suspensions of magnesium hydroxide and water, often called milk of magnesia, are used as antacids to neutralize stomach acid. Calcium hydroxide or slaked lime is used in construction, manufacture of bleaching powder, and so on.
Now, Aristotle, a student of Plato, meanwhile wrote one of the foundational texts of Western science and philosophy. It was called physics, but it was really just about nature and the world around Aristotle. He believed everything on the planet was made up of 4 elements: earth, air, fire, and water. He also thought the heavens were made of a weightless substance called ether. This philosophy was extremely influential and dominated science until the European Renaissance in the 1500s. Proof that you don't have to physically make something to be hugely influential in the study that became known as chemistry.